So last time we talked, we finished section 15.2, and you guys should be able to do up through 36, I think, from the problem set. Start with some questions there. Does anybody have any questions from the problem set that they want to talk about? Be happy to knock a few of those guys out for you if you guys have anything. Grace. Number 10. Sure. So 10 says the number of grams of carbon-14 denoted by C present in a certain substance after T years is given by blah da 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 da. What is the initial amount of carbon-14 present? How much is left after 10,400 years? And when will the amount remaining be 10 grams? Okay. So, first things first, when we read the word initial, what time is initial representing? I heard two people mumbling and I couldn't understand either one of them.
Like at the start, beginning.
Yeah, so a number though.
20.
Not 20. Hi, Megan.
Hello.
Joe. It's for you. Looks like you have an IT appointment.
Oh, Lord. It's my case. I don't even have one here.
So, okay. So again, T is representing time, right? Initial would be if there was no time elapsed, right? So what number would represent like no time elapsed? 0. So what we're going to be doing is like C of 0. Yeah. 1, 2, 1, 6, 0. So negative 0.0001216 times 0 is 0. E to the 0 is 1, right? Anything other than 0 to the 0 power is 1. And then I have 20 times 1, which would just be 20. And this would be grams. So far, so good, Grace? Okay. Part B says, how much is left after 10,400 years? Well, that's a time, so I'm just going to be plugging that in for T. So calculator time here, can't do this one in our head. So 20 times, and then to get the E on our calculator, you press second and the LN button. The LN button is just a little bit up from the on. And then I'll type in 0.0001216 times 10,400. So I get 564. Okay. And then the last part says, when will the amount remaining be 10 grams? So when will is asking about what kind of quantity if the question is a when question. Time. So we're going to be solving this equation for T when C of T is 10. Now, where is the variable located in this equation? It's in the exponent. So if you remember back to your Algebra 2 class from last year, if we wanted to algebraically solve this, what would we have to use if the variable's in the exponent? It starts with an L. No, good guess. That does start with L. Is an operation we used for like a whole chapter last year in the Algebra 2 class. Logarithm, yes, very good. Now, have we talked about logs yet this year? No. Do you suppose that's what I'm going to use to do this? No. What am I going to use instead? The graphing function on my calculator. So I'm going to graph both sides of my equation and look for the intersection. So we'll just fire up the calculator, hit the y equals button. The left-hand side of my equation is 10. I'll enter that as y1. The right-hand side of my equation is all that gobbledygook. I'm going to enter that into y2. Welcome back, dude.
Thanks.
And in place of t, we're going to use the variable x because that's the variable our calculator uses. Okay, so we got that set up. But before I go ahead and hit graph, I'm going to reset my window because, well, it's rare in these instances that our window really is suitable for what's going on. So first things first, I need to consider the x's. So I know after 10,400 years, I have 5 grams left. So that'll certainly be, a decent upper bound for my x is to just pick 10,000. I know it'll be less than that. And all we really want to make sure is that we have something suitable there where we can see the intersection. If I look at this equation, is this going to be exponential growth or decay? And how could you tell? Okay. So this is decay. That is correct. One way you could have told was, well, you started with 20, and then 10,000 years later, we're at 5. So we're definitely losing stuff. That would be obvious. But you could have told that by looking at the equation also. Since this is e to the, and the coefficient on your variable is negative, that would have told you it's decay also. Lily.
So when you're putting speed into your calculator, you do the negative x times 10 for t, for c.
For part C, the way I typed that in was just the same as it looked on my calculator. So I just...
What did you put after?
Just an x,
Oh.
the variable x.
Okay, thank you.
Yeah, no problem. Okay, so this is exponential decay, which means that the minimum for the y, the output, the minimum amount of stuff, carbon-14 that we'd have remaining would always be 0, right? Because you can't get less than nothing. Everybody agree with that? Since we're losing carbon-14, it's, decaying into some other isotope. Or possibly element. I think carbon-14 is an isotope, though. It decays into just carbon-12, I think. It's been a while. The Y max, what's the maximum amount of carbon-14 I could ever have? 20, because that's the initial amount of carbon-14 we have, and this is a decay problem. So the initial will always be the most we could ever have, so that's a good Y max. And we'll change that to 5 or something. And then here we go. So there's my line for 10. There's my decay curve. So the point I'm interested in is the intersection. How do we find the intersection with the calculator? Second trace. Good. And which command?
5.
Intersect command. That's command 5. And since there's only 2 curves that we graphed, and there's only one intersection, I can just press enter 3 times and it'll spit out about 5,700 years. Does that feel okay, Grace?
Yeah.
Yeah, we went through that pretty carefully. I hope that was pretty helpful. Okay. Peyton?
Could you do 14?
Sure. So 14 says, okay, so it's talking about this previous problem. So we've done stuff already in, looks like 11, 12, and 13 that would be related to this, right? So we kind of can't do 14 without doing the previous ones. So, or at least parts of the previous ones, because we need the models to be able to figure that out. So what we're going to do is I'm going to, all right, let's just recap what's going on. We have two cities, right? We have a population in 1990 and a population in 2000. The two cities are Austin, Texas, and Columbus, Ohio. Boo. All right. So what we're going to do is we're going to be writing an exponential function for each one of these. So that's in the term f of x equals a times b to the x. So to get our models, we're going to need to come up with a value for a and then a value for b. I'm going to be a little bit sneaky here, and instead of thinking about the times being 1990 and 2000, I'm going to think about this as time 0 and this is time 10. Now, why is that helpful to me? Because if this is time 0, then that becomes the a for one function, that becomes the a for the other, which is a lot easier than having to solve the system like we would have had to do on like 7 and 8. Okay with that sneakiness? Okay. So I'm going to call FC for Columbus and FA for Austin. Let's write it in the same order that it appears there so I don't do something stupid and put the wrong number in the wrong spot. So we have this right away. Everybody's okay? Still need to come up with B though. To get B, what I'm going to do is I'm going to use the other data point. So I'm going to plug in 6,500 or 656,562 for f of a or f of x. I'm sorry, f sub a of x. Boy, this is like a tongue twister just saying this. And then 10 for t, or x, I guess in our case. And now I'm going to solve this for b. So what do I need to do? I need to divide both sides by the 456,000 and change. Everybody's cool with that? And then how am I going to get rid of that power of 10 that's stuck on the b? What's going to cancel out an exponent of 10? A 10th root. Yep. So we'll do that to both sides. And again, when we take an even root of both sides, it creates a plus or minus. But since we're talking about the base of an exponential, we know those have to be positive numbers. So I'm just going to ignore the possibility of a negative here. And now it's calculator time. So there's a couple of different ways you could do the 10th root on the calculator. What I'm going to do is I'm going to type the number 10, press the math button, and then use command 5, which is the xth root. So basically it just lets you pick any index you want for your radical. And then 565, 562, divided by 465,622. So that gives me 101,963,4, yada, yada, yada. And I'm going to try to hang on to like all of these decimals. I'm going to eventually be graphing this. So what I'm going to do is I'm going to store this into one of my variables. I'm just going to store this one into A for Austin, so that when I go ahead and graph it, I don't have to copy all those numbers down onto my piece of paper and then type them all back into my calculator. You could do it that way. There's nothing wrong with it. Mr. Kulik's just want to write that much, you know. It's like the calculator remember it for me. So my first equation then that I have, clear this stuff out of here, is going to be 465,622 times a to the x. And then if I do the same thing for the other one, I'm just going to skate here a little bit quickly to the answer that I need. But we're really just doing the same steps as the previous one. I just don't want to write it all down because this isn't even the problem that I'm supposed to be answering. I just need to do these parts before I can do that. You know what I mean, guys? So that's there. I'm going to store this one into C for Columbus. Boo. Okay, and then we'll do that one. So I have, what's Columbus? 632, nope. Yeah, 632,910 times C to the x. Okay, so that would have been all things that we would have had to do 11, 12, and 13. I would have done that already. So it says if the population growth is exponential, which city and in which year will reach a population of 1 million people first? So I'm going to go ahead and then also type in here 1 million. So I'm going to have the line 1 million. And I'm going to change the way that these two lines graph. So I'm going to use the thick line for Columbus and the thin line for Austin. I'm just going to see which one crosses the million first. And then I'll use the intersect command to actually find that intersection. Oh, I just moved my cursor on there and pressed enter. And there's like several options that you can do. So if you press enter again, it'll give you a shade above. That's a shade below. That's a, like you can see the cursor like as it's writing it. This is it just shows you like traces it, but it doesn't actually write anything behind it. And then you're got a dashed line back to the standard. And I was going to use the thick line, so it'll be easy to tell the difference. All right. Got to change our window here first, though, because certainly 10,000 years is an unreasonable amount of time for a city to be around. I'm not really sure. I'm going to start with 100 because I don't know. Just a guess. We can always come back and make it bigger. The Y-min, the smallest population any of my cities have is 465,000, so I'm going to start a little bit under that at 400,000. Yeah. And then I care about at least 1 million, so I'm going to do like 1.25 million just for, I don't know, for grins, because I got to pick something. And I want it to be a little bit more so it'll be easy to see where it's crossing at. And then let's hit graph. So here's my Austin curve. And then here's my Columbus curve. And here is my 1 million. Oh, Boise, it looks like they're pretty close there, right? All right, well, we'll probably find the intersection for both of them and just look at which x-coordinate is smaller, since it's difficult to tell which one is actually crossing first from our picture. And I could go mess with the window and zoom in here and really be able to tell, but like using the intersect command and just leaving my window the way it is going to be equally effective, and I think maybe even just a little bit easier. All right, so press second and trace. I'm going to choose the intersect command. So the first curve, it tells me that my cursor is on Y1, so that looks good. Second curve, right now it's on Y2. That's not what I want, so I'm going to press the down arrow. That switches to Y3. That is the other curve I want. And since there's only one intersection between those two curves, it doesn't matter where I pick the guess. So I have 39.3 years for Austin. And we'll do the same thing now for Columbus and see which one is actually smaller. So again, it says we're on Y1, that's the Austin curve. I don't want to be on that, so I'll press down. Now it says we're on Y2, that was Columbus, so I'll press enter. Now it's on Y3, the 1 million, press enter. They only intersect once, so I'll just press guess. And that's at 39.2 for Columbus. Great googly moogly. Mr. Kulik, you picked a pretty annoying situation where they are like right close together. That would have been a pain in the tuchus to do all that zooming in to tell the difference between those. But the one that gets to 1 million first is Columbus at 39.2 years. Or I guess that would be in the year, if we add 1990 to that, that would be in 2029. I guess during. Does that feel okay, Peyton?
Yeah.
So it's just like, once we got the equations, it wasn't too much, but we had to go back and generate those guys to be able to answer that question. And here's one where I think if you had rounded your b value, like you know how I stored all of my decimals, if you had rounded your b value, you might have gotten really dramatically different answers. If you just like, if they're both 101 or whatever, you rounded them both to 101 or 102, which they both, I think, rounded to.
Yeah.
Then it's going to be kind of a mess, I think. Or you might have gotten a very different answer than what I got. In a test situation, I don't think I would pick something that was so difficult to tell that where if you rounded something funny intermediately,
Yeah.
you'd get a dramatically different answer than the intention. But cool. Whew. It was a workout on that one. I'm tired from talking. Ariana. Sure. All right. So 16 says the population P in millions of people of New York State T years after 1800 is modeled by the equation yada, yada, yada. What is the population of New York in 1850? So what is the T that I'm going to be using in this case that we're going to be plugging into our formula? Well, not quite, because remember it says T is the years after 1800. So 50 is what we should be plugging in there. So I'll just go to my calculator then. And we're going to do, I'm going to use the fraction command. So I'm going to do alpha y equals and pick the first option. So I don't have to muck around with like 1.5 million parentheses. Because your calculator is real dumb and it's only going to tell you to do exactly what you tell it to do, not what you mean for it to do. So if you can make it look like exactly like it looks on your sheet of paper, that's optimal. So, yes.
18 or 19.85.
Oh yeah, thank you. I missed the 7 there, huh? How'd you like that little trick? If you press second and enter, it'll give you the last thing you just typed in your calculator, so you don't have to go back and type it in again. That's a neat little trick. There we go. So we're about 1.79 million. Remember that P is in millions of people, so this number I got is actually like million. So far, so good, Ariana? Okay. What will the population be in 2010? Well, what's the T then in this case? Or 210, right? Yep, so we'll do the same thing. So that's nice because I can just do the second enter trick and go back and change that 50 to 210 and not have to type all that gobbledygook in again. Yes. So I do that. I got 19.16 million. Holy smokes, that's a lot more people. And then part C, it says, what is New York's maximum? Uh-oh. Come on. Somehow this works. I don't know why that seems to work, but anyways. Oh, the last one says, what is New York's maximum sustainable population? So to do that, I'm going to actually, this is more of a definition question than any kind of mathematics involved. So hopefully when you looked at this, you noticed that this was a logistic equation. And if you remember back from section 1, logistic equations have two asymptotes. So the one asymptote is at y equals 0. That's like the lower bound for your function. And the other asymptote is at y equals c, where that's the upper bound. And the c in your logistic equation is just the numerator. So that is my maximum sustainable population, the upper bound for my logistic. So no arithmetic or no mathematics actually needed. It was like all a definition question there at the end. Is that okay? Cool. No problem. Anybody else on questions? These were good ones, guys. These story problems can be kind of like a lot of stuff to track through and really have to understand the definition and like what you're plugging into where. And oftentimes there's some like grammar math, like knowing that initial is times 0 and stuff like that, that just like, yeah, it's good to talk about it again, you know? All right. So let's move forward then. We're going to be starting section 15.3 today. We won't finish it. So in section 15.3, we're going to start talking about logarithmic functions. We've mentioned this word a couple of times now over the last couple of lessons. We've been dancing around the existence of these things, even though we already knew they existed, because we used them last year in our Algebra 2 class. But in Mr. Kulik's experience as a math teacher, this is one of the least retained topics from Algebra 2, so I'm happy to go and spend some time doing it again. Particularly those of you that will be taking an ACT in the future. This is a topic that shows up on ACT quite frequently and is something that a lot of high school students kind of like struggle to retain. So it's a good thing to go back and look at again. All right. So what is a logarithm? Well, let's say that we have a problem like 2 to the x is equal to 4. Now, what is the value for x in this case? 2, right? That's just basic mental math. I know that 2 squared is 4. And if I say 2 to the x is equal to 8, what's the x in this case? 4. You mean 3, though, right? Because 2 times 2 times 2 is 8. But what if we had asked for, say, 2 to the x is equal to 6? Do we think it's 2.5, halfway in between? Let's check. Nope, not quite. So a logarithm seeks to answer the question, what is the exponent for 2 that gives us 6? So when we say log base 2 of 6 means the exponent of 2 that gives us 6. Right? So it's just a name for that exponent. Everybody's okay with that? We're not actually going to calculate any logarithms by hand. We're going to do it all with the calculator. Okay with that? When I was in high school, you know what we had to use instead of a calculator?
Your brain.
No, you had a giant table, and you had to look up the values of logarithms off of a table. It was super annoying. It's the same way you had to do sine and cosines, because you did not necessarily have calculators that had those things programmed into doing it. Cool, right? You guys are living in a golden age of technology, and you don't even know it. So let's formalize this with our definition as soon as I pound on my desk and try to get the camera to come back on. Somehow that works. I don't know why it works. It really bothers me, but just do what you got to do. All right, so we say that for b greater than 0 and not equal to 1, the following, that b to the y is equal to x is equivalent to log base b of x equal to y. So again, when we read this symbol, we read this as log base b of x. I guess should highlight the rest of that. Okay. So the b here is the base of the logarithm. Okay with some basic vocab and this basic definition. So this definition is pretty important. It's one that you'd want to remember. To help us remember this, let's do a couple of examples. So let's say we wanted to do log base 4 of 16. And let's say that's equal to, let's just say equals x. So if I rewrite this as an exponential equation, so I'm going to be using this rule above, I'd say 4 to the x is equal to 16. Everybody's cool with that? This equation now is straightforward to answer. What does x have to equal in this case? Dos. In Espanol. That's about the limit of my Spanish knowledge right there. Is everybody okay with how we did that? Is I took the logarithmic equation, turned it into an exponential equation, in which case it, in this case, was a mental math problem. So let's say we have log base 5 of square root 5. Again, I'm going to think about that as equal to x. So what exponential equation does this make? Who can tell me how to rewrite this as an exponential? Joe, go ahead.
Should we say 5 to the x is equal to, do we keep the square root of 5?
Yep.
Square root of 5.
Exactly. That's good. So this is now kind of a definitional question. Does anybody remember What exponent is the same as a square root? This was something we would have talked about last year. What was that? Not 3. It's actually a fraction. Not 1/3. 1/2. Yeah. So the rule that we're using there is this one, that the nth root of x is equal to x to the 1 over n. Everybody's okay there? That ring a bell from Algebra 2 class last year? And that's a nice one to hang on to as well, as that's a commonly would show up on something like an ACT, where that would be a potentially useful rule to remember. All right, next one. How can I rewrite this? 3 to the x, 1 over 27. Yes, sir. Yeah, absolutely. Sure. Now this one's a little bit trickier. What are you talking about, the stuff in blue?
Yeah.
That was just the rule that I used in
No, I
part
know.
B.
Did you write an M there?
Yes, that's an
Okay.
n. Yes. Yeah. That n is the same as this n. Yep. No problem. I just was talking about something else, so when we changed gears, I was just like, no, it's okay. Totally okay. If you want to track back and clarify, my penmanship is sometimes less than spectacular. So, no problems. This is a little bit tricky here, right? It's maybe not obvious right away what that is. What if we rewrite 27, though, as 3 cubed? Does that help? So 3 to the x equals 1 over 3 cubed. What should x be now? This, again, another rule of exponents that we might remember from Algebra 2. Hopefully. X needs to be -3. Why negative? So the rule that we're using here is that negative exponent makes a reciprocal. Does that ring a bell? Hopefully, these exponent rules, they pop up all the time. So it's a good thing that we're reviewing them, right? Oops. Okay, what if we have log base 12 of 1? How can I rewrite that as an exponential equation? It's a good time to ask since Joe's in the bathroom and can't answer this for all you guys. Anybody want to take a stab at it? No pressure. It's okay to be wrong. It's not a big deal. It's how we learn. Very good. 12 to the x is equal to 1. So what's x? 0! Yeah. Again, remember that this property, we mentioned that already once today. Anything to the 0 power other than 0 is equal to 1. 0 to the 0 is undefined, in case you were curious. Okay? What if we have log base 8 of 8? How would I rewrite that as an exponential? Eight to the x is equal to 8. Great. So what would x have to be? 1. Excellent. Okay. So if we kind of summarize what we've just observed here numerically, we can come up with a couple of basic properties for logarithms. So the log of any base of 1 is going to be equal to that's what we observed here on D, right? It's equal to 0. Again, this is equivalent to saying b to the 0 is equal to 1. Why don't I have to worry about b being 0? Well, because when we defined our logarithm, we said that b's have to be greater than 0. So I don't have to worry about that possibility. It wouldn't be wrong to write b can't be 0, but it's implied because it's the base of a logarithm. So those have to be positive numbers. Next one, we have log base b of b, and that has to equal, this is just like letter E, right? So it's got to equal 1. Very good. Which is the equivalent of saying b to the first is equal to b. So if I have log base b of b to the y, that has to equal, well, this is just like letter A. It's got to be y, right? This is the same thing as 4 squared, and our answer just comes out to be 2. So it's basically the idea there is that log base b is going to cancel the exponent base b. But this is basically just saying b to the y is equal to b to y. Oh, shocking. So surprised. And the last property, we should say, is basically the reverse idea of this. So here we're saying that log base b is going to cancel exponent base b. We can also say the reverse, that exponent base b will cancel log base b, because that's really the equivalent of saying this. Okay. One more topic and we'll stop a Ruski. Sound good? All right. So there are 2 special logarithms. And we give them special names. The first one is called the common logarithm. This is log base 10. But we don't ever write log base 10. We just denote this as log with no base. So if you see log with no base written, what is the base? 10. So if you see log, that is base 10. What base does log have? 10. Okay. I realize that it's repetitive, but like if I say it 3 times, everybody hears me. Even the person that's like doodling away, daydreaming or whatever. You hear it 3 times, somebody's got to hear it, right? The other one is the natural logarithm. That is log base e. And again, we remember e from the other day. That's that irrational number. I don't know. I don't remember what that decimal was actually. It's 271 something, right? And this we denote ln. Now, when I write my logs, I always write cursive. And the reason I'm writing cursive there is because the letters log resembles the numbers 10g, or 109 even in cases. If I write it cursive, they no longer look like numbers. If I write the letters ln, that looks like the number 1n if I print it, right? That's why I'm writing them in cursive. Everybody's okay with that? I would encourage you to do the same. I frequently see students halfway through a log problem where they're printing their logs. The L's turn into 1s and the zeros turn into, or the O's turn into zeros, and weird things start happening, and I start shaking my head and go, oh my gosh, what did I do? Okay. Let's run through a couple of quick examples, and then let's get out of here, okay? So let's say we have log of 1,000. Again, I'll set that equal to x. The base on this is 10. So 10 to the x is equal to 1,000. So what's x? 3, right? 10 times 10 times 10 is just 1 with 3 zeros after it. Right? Right? Right. Okay. What if we have log of the 5th root of 10? So this is going to be what exponential equation? 10 to the x is equal to the 5th root of 10. So what is x in this case? It's not 1/2 because it's not a square root. It's a 5th root. 1/5. There you go. We doing okay here? What if I say that d is, or what if I have e to the ln of 5? What about this? No, I would probably just use this property 4. Right? Because I have that situation, right? Because what's the base on ln? E. So this just turns into Basically, this is all I'm thinking about, is just exponent base cancels log base. 5's all that's left. That's nice. So what if I have ln of y is equal to 5? How would I write that as an exponential equation? I'm just using the basic definition. So what's the base of the logarithm here? So I'd say e to the 5th is equal to what? And e to the 5th is something we do on our calculator, right? Okay. What if I have like the natural log of 12? Great. So e to the x is equal to 12. But what is x? Not a mental math problem anymore, right? How do I do that? What if I just want to type in the natural log and get a number out of my calculator? Well, the ln button is on your calculator, just a little bit up from the on. And just do like ln of 12. Press enter. That's what the natural log of 12 is. What if I wanted, log base 8 of 17? Well, one way I can do this is if I press the math button and scroll down and find the log base option. That allows me to type in any base I want. And there's log base 8 of 17. Is that decimal? Right? So what it's saying is just that 8 to that decimal is going to give me 17. And this feels like a good place to stop. So at this point, you guys can now go, we're up through 36. We can now do all the way to 68. What's today? Wednesday? Yes, that'll be on. Oh, let me think. So let's make it due on the next one. Because Thursday's class won't have a chance to see me again before the weekend. So let's do that. That seems like better. I'll update the calendar and I have to change that stuff on the board, and I'll get it on PowerSchool, or what is it called? My Notre Dame is what we call it now. You knew what I meant though, right? I'm still living 2 years in the past or whatever. You living in the past, man. Everybody cool there? All right.